let's say some distance d away from one side. So now you're going to take a piece. So I'm still assuming that the rod is uniform, right? So I'm going to take a piece here. Then I'm going to say this piece creates an electrical field like that. I'm going to make it kind of big, right? But here, there's no symmetry. In other words, the piece here is going to create an electrical field smaller because it's farther away. So, and they don't cancel. They just keep adding to each other. So the biggest electrical field is created by the nearest piece, and the smallest electrical field is created by the farthest piece, you see. So they just completely add up, okay? So then what would be the equation of the electrical field? Is going to be K dq over R squared, where R is the distance from that piece to over there, from here to here. Okay, so if my coordinate axis is in the middle of the rod, xy, the distance from here to here would be x. Right, so now I have to come up with an expression for R. What's the distance of a certain piece of the rod from the point where I'm trying to find out the electrical field? So what's this distance R? Let's see here. If this distance is given as D, and that distance is X, oh, and this distance from here to here is L over 2.
So you're trying to find the point from the point.
Yeah, I'm trying to find an expression for the distance of any element of the rod to that point.
Okay.
If that element of the rod is the X distance away from the origin, right? So you're basically putting together the fact that this is X, this distance from here to here is D, and then that's L over 2, and then this is R.
But
Okay,
R
so,
is not constant, right? R changes.
Oh yeah, of course R is not constant, because if this element is here, then R is farther away.
Right.
But the equation we come up with should be able to handle all that.
Right.
You see?
Okay.
So I'm gonna say L over 2. Oh, okay. Here's the idea. I'm gonna say L over 2 plus D. L over 2 plus D. Because the L over 2 is the distance from here to the end of the rod plus that distance to that point, must equal to X plus R, right? Which is the distance to that point, right? To that element, and then R is the distance from the element to that point. So you see, this distance plus that distance must equal to this distance plus this distance. Okay, then I can come up with an expression for R. Then I can put that there and square it.
And what you created takes account if it's on the negative side?
Oh yeah, yeah, it will take into account. Notice if the X is a negative number, then it's going to be minus a negative. That means R is going to be further away. Yep, okay. It should take that into account.
It does, okay.
Oh yeah, yeah, it does. Yeah, that's cool. Okay, so then dE is going to be K, and then I'm going to use the dQ's lambda dx again. Okay, and then you're going to have L over 2 plus D minus X squared. This one I'm going to do similar. For uniform charge rod, I like getting a general answer and seeing if my answer makes sense. But once we go to non-uniform, then we'll just get a directly a numerical answer right away. So then I'm going to integrate that. This one, you can't go from 0 to L over 2 and double it, because the electrical field contribution from the left side of the rod is weaker than from the right side if I'm on this side. So it's not symmetric. So you got to go from negative L over 2 to L over 2. And then if the charge density is uniform, it comes out of the integral. as a Q over L, right? And then negative L over 2 to L over 2. Okay, so now we go back to the integral. For this one, the power doesn't come out 1/2. It's actually a square. Okay, so then we have L over 2 plus D minus X squared. Okay, and then it's going to be negative L over 2 Okay, that's the answer. It's L over D, L plus D. L over D, L plus D. So L over D, L plus D. It came out pretty easy looking. So then it's just the L cancels the L. Okay, now what are the limits of that? So if I'm close to the rod, when D is small, what's the behavior? Limit as D is goes to 0. So remember, when D is being added to something and it's small, then you could ignore D. Then you just have left this D and then L. Oh, it's again linear. What was the other one? 2KQ over DL. 2KQ over DL. And then this one is KQ over DL. Oh, it's about half the strength of the other one.
Professor, what do you mean as D approaches 0? I thought D was fixed. I thought D was the closest point from the rod to the point.
Yeah, but that point where I'm trying to find the E field could vary, right? So
you're saying what
I
is the
could
E field
find
at point D?
Yeah, I could find let me see.
Oh, so that would be your strongest. So you're finding the strongest
Okay, so
electromagnetic field, right?
yeah, so then I could let's see here. Right there, you see, I could have D, this one, the D is 0.1 centimeter, 710, and then 0.2 centimeters. Okay, so the behavior of the electrical field when I'm near should be linear again. But it looks like it's half the strength of this one. So let's say 20 centimeters away, what is it here? 740, right? 20 centimeters away here should be about half of that. Yep, it is. Yeah. Oh my gosh, it works. It's half the strength. Yeah. So it's half the strength of this one because it's missing the 2. You see, it's missing the 2 here. The other one is 2KQ over DL. But it is also linear, just like the other one. So if we made a plot, of it, you know, at 10 centimeters, 20 centimeters, 30, 40, 50, so on, we should see that it's linear. Here's what, without making the plot, we can just compare 2 of them. Let's say this is 30 centimeters away, right? It's 250, 30 centimeters away. Then 60 centimeters away, it should be about half of that. No, it's not. That means the linear behavior only is true when it's close to it. Let's see, 20 centimeters away, it's 380. 40 centimeters away, half of 380 would be what? 190? Not quite. So the linear behavior only lasts probably when you're close. You see what I mean, Joy? So if I'm 10 centimeters away, the electric field is 920. 20 centimeters away, 418. Not even, right? Let's see here. 920. Oh, no, yeah. Probably this is about half of that. Yeah. But it dies out. So the linear behavior doesn't last that long. Here it looks like it lasted longer, the linear behavior. You see how you can tell by drawing the electric field lines. Here the electrical field is more straight, concentrated. Here they diverge out quicker. So the linear behavior here doesn't last as long as the linear behavior here.
What do you, when you say last or doesn't last or lasts longer, what does that really mean?
It means the divergence of the electrical field. You see here, the electrical field diverges like this, and the strength of the E field here dies out quicker. Whereas here, because the rod is all inclined this way, the electrical field behavior here lasts, like in other words, if I'm, let's say.
So it's like you're saying it's more concentrated.
Yeah, you see, if I'm 1 meter away, look at the strength of the E field.
Right.
75. Here, 1 meters away, it's already dying to 43. You see, 2 meters away, it's 14. Here, 2 meters away, so 1 and 2 is 21. So the strength here is stronger. Not that much stronger, but it is stronger. You see, and that means the linear behavior of the electric field lasts for a longer period here than the linear behavior here.
Okay, yeah, that makes sense.
Yeah, because the electrical field is weaker and it diverges out. See, I wish they had drawn E field like right here close by. That would be nicer. But it would be nicer to have more fields drawn. And later on, when we talk about voltage, equipotential, in the chapter 23, we'll also talk about the voltage lines, equipotential lines. And you'll see that the voltage probably dies quicker this way too, than the voltage this way. So if I take the voltage reading, 83 volts, but if I go on the other side, the voltage also dies down quicker. You see, 60 volts. So I have to go closer to be 83 volts. You see. But whereas here, over here, it's still 83, you see. So the voltage sustains more here, just like the electric field sustains. Man, this stuff is fun. Oh, man. Fields is all where it's at. Fields, gravitational fields, magnetic fields, electric fields. Oh, okay, now let's find the electric field behavior when you're far. So when you are far, then you ignore the L. Okay, then you have our famous KQ over D squared. Okay, so you see the linear behavior quickly turns into a square behavior. So similarly to the middle of the rod. So that means if I were to check the electrical field here, that's 1, 2, so this is, let's say 1 meter away, 44. Now if I go 2 meters away. Is that linear or more like a square function? Look at that. I went from 1 meter, it's 44. If I go to 2, the strength is 14. So is that a square function? So 1 meter away is 44. 2 meters away is 14. So is that a linear behavior or a square behavior? So for linear behavior, this would have to be what? 22, right? 22 newtons per coulomb. So it's definitely decayed quicker than a linear. But is it a square behavior? 44. So what would it have to be in order to be square behavior? If I'm doubling the distance from 1 to 2, 44 over 2 squared is 4, it's 11. Okay, so it's not decaying yet as quickly as a square behavior, but it is closer to the square behavior than the linear behavior. You see? So remember how I said in the middle, it's like a general relationship. So in other words, from 2 to 4, I'm still in the middle where it's not a square behavior or linear. Linear behavior probably occurs here. And here is some general behavior. Now, if I go to, let's say, 2.5 meters, this is, no, this is 1 meter, 1.5 meters, right? So it's 23. 1.5 meters is 23. Then 3 meters, so a half, and then another one. 3 meters is 7.38. So do you see, I'm trying to see when does the square behavior start, kind of kick in. Has it already kicked in by, see, I compared 1 and 2, and I'm kind of close to a square behavior, but not quite. How about 1.5 and 3? If I double it, well, definitely it's not linear because this would have to be 11, half of that to be linear, you know. So is it already square? 23 divided by doubling. So 2 squared, this is 4. Okay, but not quite yet. That's about, what is that? 6. Okay, it's not decaying yet as a square behavior. You see that? Let's go one more. Let's compare 2. 2 meters is 14. And then, so 2 meters is 14.8. And then 1, 2, that's 4 meters. 4.48. Okay, now is that square? 14.8 divided by the 2 squared. So I'm doing the distance squared relationship. So if I'm doubling the distance, then I'm going to divide it by 14.8 divided by 4. What would that be? Oh, that's probably, no, not yet. Okay, not quite yet still, you see. So I can kind of keep doing that until I find out, oh, okay, the square relationship has really kicked in.
Why do you think, or why do you expect there's going to be a square relationship?
Oh, I just proved it. Well, first of all, by logic, when I'm far away from a rod, either this way or this way, the rod should look like a point charge, right? And so its behavior of the electrical field should be decreasing as 1 over the distance squared. Right?
I would think
I'm
only
far away from something that has a dimension. Its dimension begins looking smaller and smaller, and the behavior of the electrical field and the behavior of the voltage created by that charge begins resembling the behavior of a point charge. In other words, when I'm far away from this rod, it's almost as if the rod looks like this to me.
Right, right. Yeah, I understand that, but
You see,
are
it's
you
like,
trying to compare?
you see. Now notice when it looks like that to me, what do the electric field lines look like now? Well,
Right,
this is a
they're radiating in every
You
direction.
see how they're radiating more spherical?
Right.
Yeah. So now, if I find out the behavior, see now the rod looks like this to me. Imagine I'm like 100 miles away, you know, and I'm here. So now, if I am certain distance away, let's say here, and I double it, what should happen? So take any distance. That's a good question that you gave me because it led me to show this, you know. That's why I like questions.
Right, but what I'm trying to get to is that you will have the behavior of a single point charge if it's on the right side of it, where you see a
Or
linear
anywhere
pattern.
on the right side, on the center.
Right, but wouldn't it be that you'll get that effect a lot quicker
Where?
if you had it to the right? Say you had the linear rod and say you put it to the right of it, you'll
Yeah.
see a point charge rather stronger than if you had it on top.
Oh, the middle, you're saying?
Yes.
The middle, it seemed like it started appearing way up here.
Yeah, like some further distance.
Yeah, it started appearing. Yeah, here I don't know. It seemed like I have to go maybe one more step away. Yeah, to get that.
I'm only asking because I'm trying to understand what you're trying to compare a little more.
Oh, well, because I'm trying to compare to the behavior of the electrical field of a point charge. You see how it's radial? So now anywhere that I go, let's say that this distance is, see, I don't even have to go in the middle anymore. I just go, okay, that's 155 centimeters. The electrical field is 34, you see? Now if I go, what's double 155? 300, right? Okay, so if I go 34, if I go 310, let's say.
Yeah, that's good.
Okay, so now it's 9. That should already be a square behavior or close. What was it? 34. So then I double the distance, right? I double the distance. What was it? 34 over there? 34 over 4. What do you get?
34 over 4.
34 over 4.
8.5.
Okay, it's not quite square yet, but it's close.
But yeah, I see it trending that way.
Yeah, you see you're trending. I would have to place these right on top of each other. That means you're so far away from the rod that it looks exactly like a point charge. You see, like that.
Almost.
See, now the electrical field look very radial.
Very, very spherical.
Very spherically radiating outward. You see? You see that? Now if I do the test, go to 155.
So you're doubling the distance or you're squaring the distance?
No, I'm doubling the distance, but then the 1 over distance squared would be 1 over the 2 squared. That's always a quick check you can do. Double the distance, figure out the electrical field at some distance, that's 37, and then double the distance to 310. What was it, 37 over there?
Yes, it was 37.
So now divide 37 by 4.
37 divided by 4 gives us 9.25.
Oh, I see that. 9.29.
Yeah, approximately.
There you go.
Okay.
Now, so that means a point charge has a sphere, has a 1 over distance squared, right?
Mm-hmm.
Yeah. And the rod begins looking like a point charge when you're far away.
Right.
I kind of compare this to sometimes when people say, give me another kind of thing that I can use this as an analogy to. I give them the fluorescent light bulb. You know how a fluorescent light bulb is a long, elongated rod?
Right.
So I say the light intensity coming from the fluorescent light bulb looks like the electrical field of a rod. But as you go far away from the fluorescent light bulb, the light intensity should start dropping as 1 over distance squared. So if you want to do this test at home, get your iPhone, download an app that measures light intensity, okay? Turn off all the other lights in your house except one fluorescent light bulb. So on a dark day, you know, like at night, you know. So just take one fluorescent light bulb, long, elongated, take the iPhone app, measure the light intensity coming from the fluorescent light bulb. I believe it'd be units of lux. There are apps that you can download on your phone. So then measure it, let's say every 10 centimeters, you know, start up really close to the light bulb, then 10 centimeters, 10 centimeters, 10 centimeters, keep going, and then plot that as you go far away, as you go all the way like to the other side of the room, you know, you will exactly see the similar behavior. You'll see first linear, the intensity will drop linear. Then in the middle, it won't be linear or square, right? Then as you go farther away, it'll be a 1 over distance squared. That's the closest you can get.
If you wanted to...
Well, another thing you can do is take the light, a meter and put it next to your, the screen, the brightness of your computer screen. Oh yeah. Except the brightness of the computer screen will be first constant because the computer screen will behave like a plate charge, not a rod. So it will first behave as a plate, and then as you go farther away, it will start looking like a point charge. So you can actually do this with the computer screen. Measure the brightness of the screen every, let's say, 5 centimeters. Or your TV, or even your TV brightness, you know, plot that. Go 10 centimeters, 10 centimeters, keep going farther like that. I'm giving you a good idea for an extra credit home lab you can do, right? Hint, hint.
Professor, if you were to make some kind of a reference to astronomy, what would be one? Would it be like a protostar, maybe?
A reference to astronomy.
I know we don't have nothing linear like a rod, but
Well, I mean, you have galaxies which are elongated, you know.
But what does that tell you? I mean, I'm just curious if there's something we can question about it.
I guess we could say if you're close enough to the galaxy, where the galaxy looks like an elongated rod in the sky. See, we're not really that close enough to. They look more like point objects for us.
Right.
So their brightness is 1 over distance squared. But if you were more like closer, and the galaxy was really close, it would kind of look elongated, you know. And you can kind of see that. I guess you could say the image as seen through the Hubble, you can kind of see the elongation, you know. And also the electrical field that it gives off, all the energy that it gives off is 1 over the distance. If you're close to the galaxy, it dies out as 1 over the distance.
Oh, yeah. Cool.
Yeah. But when you're far from the galaxy and it looks like a point charge, then the electric field and the brightness dies down as 1 over distance squared. Yep. Okay, so, and with the rod, you could also get a direct answer So numerical answer, if we wanted the electrical field at any distance, then you would just get, so instead of this integral, we would just put numbers. Let's say I wanted to know the electrical field 1 meter away from the side of the rod. So then you would just do, let me see, let me write it in this space so I can see it. So let's say I wanted 1 meter away. Okay, then I would just do E field would be 9 times 10 to the 9th. And then the Q would be 10 times 10 to the minus 9, 1 meter. Now go minus half to half. And then dx or half plus 1 minus x squared. So it's the same idea, except this is directly getting the numerical answer. A half plus 1 minus x squared minus half to half. Minus a half to a half. And then whatever the integral gives me, I'm going to multiply it by k times q over L. And then this just gives me nothing. So let's see here. Oh, I would have to integrate that first. So half plus a 1, that give me 1.5, right? So then integral so I would put here 1.5 minus x squared, and then minus half to half. Oh, you just exactly half. And then I would multiply that by what? So it just gave me a half. Now I multiply it by 90. There you go. And then that's just 45. Is that the answer? Let's see here. Okay, let's elongate it back again. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. It's hard to do this. You have to make it very uniform. Okay, so I said 1 meter away. So 1 meter would be right there, right? What did I get? 40, 45? Oh, wow. Very close. Nice, 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 nice. Okay, now let's do non-uniform rod. So for example, let's say the rod is more charged towards the ends.